All right, so the next section in the notes is about exponential growth. Oops. All right. All right, so the next section in the notes is about exponential growth. So this is section 7.8 in uh, the daily videos in AP Classroom. So if you need extra review or extra instruction, that's where you're going to go. So for exponential growth functions, the more you have, the more you get. For exponential decay, the less you have, the less you lose. Quantities that grow or decay by a factor or percentage at a regular interval are called exponential. Right? They have a common ratio from number to number. Either you are dividing each number by, a number between 0 and 1 for B representing decay. Okay. So B will be greater than 0 but less than 1 for decay. And then, of course, for growth, your B is going to be greater than 1. In both cases, it won't be 1 because if you raise anything, if you have an exponent with a base of 1, it's just always going to be 1. 1 squared, 1 cubed, 1 to the 5th. Okay. This can be stated equivalently as the rate of change of a quantity is directly proportional to the quantity itself. So the rate of change, which is the derivative, is directly proportional which means multiplication, right? Directly proportional, multiply to the quantity. If they said it was indirectly, it would be division. Directly proportional is multiplication. Mathematically, we state this as the derivative is equal to k times y, where k is either the growth or decay constant. Okay, and y is going to represent, in exponential, we know that y represents technically the a, which is the y-intercept. All right, let's solve the separable differential equation when it's in an exponential form. So dy dt, this is basically saying that the rate of change, which is the derivative of y, right, is directly proportional to y. Now k is going to be our constant in this case. So once we separate it, we want to get the y with dy, and then the dt with k. So once we do that, we're going to divide both sides by y and multiply by dt. Okay, I'm just doing it all in one step. Now the y's are gone on this side, dt is gone on this side. So here we are left with 1 over y dy equals k dt. Remember, k is a constant, it's not t itself. So now that we've separated, next step is to integrate. The integral of 1 over y, we know, is ln of y, absolute value. And the integral of a constant is going to be a constant times that variable, which is t, and then plus some constant c. Now, if you guys recall, we got to solve for y next. And how we do that is everything gets raised with a base of e. And the reason why this happens is because e to the ln of y will cancel out the e and the ln, and you're left with just y equals e to the kt plus c. Recall, it's going to be e to the kt times e to the c. And e to the c is just going to be c. We'll bring it to the front. And that's why the function itself is exponential. Now, specifically, is this a growth or a decay? Just by looking at the base, e is about 2.7, so this is going to be an exponential growth function. All right, example 2. Bacteria in a culture increased from 400 to 1600 in 3 hours. Assuming that the rate of increase of the population is directly proportional, so the rate of increase of the population is directly proportional to the population. By them saying the rate is directly proportional to the population, basically they are telling you that dy, we can call it, because this is population, right? We can call it dp dt, right? The population, the change of population over the change in time is equal to some b value times the population. So now we know that all differential equations in this form, I don't need to solve it again, but it will end up looking like this guy right here. So I know that if the derivative is a directly proportional derivative to the value that we're looking for, therefore our p in this case is going to equal c e to the kt. So I know that this is going to be the function. Now we're given a piece of information, 2 pieces of information, right? We're given 2 pieces of information to figure out what our c is. So now that we have this, we want to basically figure out what is our c. The 2 pieces of information that they gave us is that t equals 0, p is 400. The other one, we could use it, we could not. At t equals 3 hours, p is 1600. We may or may not need it, right, at this point, but let's see. So we got to figure out what c is, sorry, and I forgot. We also got to figure out what is k. Okay, we have 2 unknowns here. So we got to figure out what is c and what is k. So the first thing I'm going to do is solve for c. Now, in order to solve for c, I will need to get rid of kt. And that is done when t is 0, right? 0 times k is going to be 0, and e to the 0 is just going to be 1. So by using this first piece of information, I can set up 400 is equal to ce to the k times 0. And from this, I get 400 is equal to C. Now that I've solved my C, I can solve for my K value using the second point. Remember, we've talked about this before. When you have two variables to solve for, you will need two pieces of information to do that. So the next part is going to be 1600 is equal to, now we know what C is. So that's going to be 400. E, and then we still don't know what K is, but T is 3 when P is 1600. Solve this, divide both sides by 400, right? 16 divided by 400 is going to be 4. I don't know why. 40. Okay. 4 is equal to e to the 3k. How do I bring that k down? I'm going to take the ln of both sides. So now ln of 4 is equal to, this 3k comes down, ln of e is just 1. Divide by 3. Ln of 4 over 3 is equal to k. And now that we have our k value and we have our c value, I have an equation of the model. And that is going to be y, we used p. That's going to be p equals 400 e ln of 4 over 3 t. And that's it. So now that we have a functioning problem, we can solve part B. Find the number of bacteria at the end of 6 hours. So basically, what is P when T is 6? All right. So this is a calculator problem for obvious reasons, right, ln? If it's not a calculator, it has to be a value that you can actually solve for. Okay, so I plugged in 6 for T. Once you do this in the calculator, you should get 6,400 bacteria. So after 6 hours, there is 6,400 bacteria in the culture. All right, example 3. Radium 226 loses its mass at a rate. Okay, again, they're telling us the rate. So this is going to be a dy dt. It's directly proportional to its mass. So this right here tells us that it's exponential. Our rate means that it's going to be something with respect to time. And in this case, you can use dy dt every single time if that makes it easier, or you can give it its own name so that you know what values you're dealing with. I'm going to call this dm dt because it is the change in mass over the change in time. So we want to find the formula for the mass that remains after t years, which basically means find the equation for m of t. And the way we can start this is we can start with the information that's given to us, and that's dm dt is equal to k times m, right? And knowing that this is exponential, I don't need to solve this differential equation again, but I know that the function will be in the form of m equals CE to the KT. So now I need to figure out what is C and what is K. And again, they're giving us two pieces of information here. Okay, we have two pieces of information. Is the half-life. It has a half-life of 1590. So if we remember, what is half-life, right? Half-life means how long until half of half is left, half of the original sample. Okay, so half-life is 1,590 years. And we start with a sample, so I'm going to write that down. The time it takes to cut sample in half. And if we start with a sample of radium-226 with a mass of 100 grams. So the two pieces of information that is given is that when T equals 0, our mass is 100 grams. And then this half-life tells us that the mass is 50 grams when T equals 1590, right? So the Y value gets cut in half. That's what makes it exponential. Now, you will start seeing a pattern, right? Whenever they give you T equals 0, and that's going to be 100, obviously that's going to be our C, right? Because if we plug in 100 equals C e to the k times 0, it's always going to be what C is. So C is 100. And we know from all other exponential functions that the y-intercept is represented by the variable, the coefficient at the beginning of an exponential function when t is 0. So we got our C, and now we're going to use the second point to solve for K, knowing C. So for the second point, 50 equals 100 e to the k times 1590. Divide by 100, take the ln of both sides. Okay, so divide by 100, you got a half. You take the ln of both sides. I'm just doing a bunch in one step, right? Divide both sides by 1590. Okay, because this is a fraction, I'm going to write this like this. Now, that is basically our K. With ln being a fraction, we do have to remember our log rules, because if this was a multiplication, a multiple choice problem, they will probably split this up. All right. And the way that they split this up is going to be ln of 1 minus ln of 2. And look at this. What is ln of 1? 0. So ln of half is going to be just negative ln of 2. And then, of course, over 1590. And now I have my K. I have my C. So my final answer is going to be m equals 100 C e to the negative ln of 2 over 1590. And as long as you get this correct, Find the mass after 1,000 years. So what is M when T equals 1,000? I'll let you guys plug this into the calculator. And remember, even if it is a calculator, you have to show the setup. You have to show the setup and then identify what it is equal to or approximating if it's a decimal. And then for part C, what will the mass be? When will the mass be reduced to 30 grams? So here they gave us the mass. And we want to figure out the time. So again, this is a calculator problem, but there's some work to be done before you can actually use the calculator. So setup is not going to be enough. But using this formula, we know what M is. M is 30. Sorry, I don't know why I put a C here. I just noticed that. And I forgot my T. Okay. Now T is in the exponent, so we obviously need to bring it down. But before we bring it down, we need to isolate the stuff that's in the exponent. So the first thing we're going to do is divide both sides by 100. So that gives us 3/10, right? And that's equal to E raised to the negative ln of 2 over 1590 to the T. How do we bring that T down? Take the ln of both sides. So now we got ln of 3 minus ln of 10. Neither one of those cleans nicely, so we're just going to leave it as ln of 3/10 for now. Anyways, it's a calculator problem, so it doesn't really matter. Equals, that's gone, negative ln of 2 over 1590 T. Multiply both sides by 1590, divide by negative ln of 2. Will give you your T. And once you get to this point, now it's calculator problem. And when you plug this into the calculator, you should end up with about 2,761.775 years. Remember, don't forget your units with story problems, okay? All right, example 4 is now with oil. Okay. I thought it was money. Suppose that the amount of oil pumped from one of the canyon wells in Whittier, California decreases at a continuous rate of 10% per year. Okay, so something is decreasing at a continuous rate. So here they are giving you what the B is, right? But in our case, the formula is exponential. And they are basically telling you what K is in our differential equation. So looking at this problem, you have to know that this is going to be an exponential problem. Now, it wasn't similar to what they were saying in the previous ones, right? But we know that if something decreases at a continuous rate, that means it is going to be a proportional decrease all the way through. Now, normally, because we know that exponential is in this form, AB to the X, I could just go directly to the function. But they only give me the rate. They don't give me anything else. I don't know what A is. I don't know what B is, right? I don't know what X is, what Y is in order to fill these parts in and solve for one, both, or all of these variables. But now we know that we can start with a differential equation. dy dt, knowing that this is exponential, I can start with the differential equation, and then k is going to be our rate of 0.1 times t. So now, knowing that it's an exponential, I know what this guy looks like. So e to the 0.1 times t. Okay. So from here, we have a function. We have a function for what this should look like, right? Now, when will the well's output, so output means the y, fall to 1/5 of its present level? So 1/5 of the level right now. Now, we don't know what the present level is. Okay, so present level means at t equals 0, I don't know what y is. So we're gonna need to utilize this value right here if we could. To figure out C. Because we just need to find C, right? We just need to find C. So if the output is going to be 1/5, I could use just the idea of dividing something by half, right? By 5, sorry. Dividing some number by 5 and figure out what my function might look like. So given this, and remembering that C is going to be the initial value. So given this, bear with me, and C is the initial value. All right, if C was 5, could we figure out what Y is? Yeah. So if C, which is the present level, let's pretend, right, which is 5, then Y is going to be 1/5 of 5, which is going to be 1. So having this is going to allow me to solve for T, right? So I just picked a level, a starting level that was easy to use the fraction that was given, and I got an output. I could have picked 10 and 2, right? I could have picked 20 and 4. All right, but this is the information that was given. All right, so from this, obviously we divide by 5. So we got 1/5 equals e to the 0.1 t. Take the ln of both sides. And in this case, ln of 1 minus ln of 5 is equal to 0.1 t. ln of 1 is 0. Divide both sides by 0.1. This is calculator. So t is going to be approximately, I don't know, Can you guys figure that out and plug it in? And I'll check your answers tomorrow. All right, example 5. Suppose that a population of fruit flies grows in proportion to the number of fruit flies in the population. So it growing in proportion means that this is an exponential function, specifically an exponential growth function. So proportionally growing to the population. So dp dt is equal to k times t. Yep, because it's proportionally growing to the number of fruit flies in the population. So dp dt is equal to k times t. Now, this question says if there were 100 flies after the second day, so the information that's being given is when t equals 2, p equals 100, and 500 flies after the 4th day, when t equals 4, p equals 500. How many flies were in the original population? So this question is asking, what is the population when t equals 0? Now, in order to figure this out, we have to, we need the original equation. All right. Now, we know that this is going to be exponential, so I know what my equation should look like from my differential equation, and that's P equals CE to the KT. Now, if I plugged in 2 and 100 and 4 and 500, I'm not really going to be able to, you know, get rid of the e to the KT. Okay, so this is a little bit harder. I think there are definitely different ways of solving this. One might be easier than the next. We're gonna leave this for class. I need to do a little bit of research before I see the way that the book does it, but I want to try something before I teach it. All right. And then example 6 and 7 deals with Newton's law of cooling. Now, if they ever give you Newton's law of cooling on the exam, because it's not something that you have to memorize anymore, this will always be given. So the formula for Newton's law of cooling for the differential equation will be given. But Newton's law of cooling states that the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature in the surrounding, right? So if you put a bowl of soup on the kitchen counter right next to the stove, it's gonna cool much slower than if you took that bowl of soup and you put it in the freezer. That's the idea. All right. So the change in the temperature over the change in time is directly proportional to the rate times the temperature and minus the temperature surrounding. So find the general solution basically means separate and integrate, right? So we're going to separate and integrate. So I'm going to do this in one step. To separate, I'm going to put dt over here, and I'm going to bring over 1 over t minus t to the s with capital T over here, and this is going to be with k. All right, once we've separated, we can integrate, and we know that 1 over a quantity, a linear quantity, is going to be ln of t minus ts equals kt plus c. Now this looks very familiar, right? It's basically the same as exponential, because we raise both sides to e. The only difference is that when you do this, you got t minus ts is equal to ce to the kt. And here we are not solving for ts, we're solving for t. So t is equal to ce to the kt plus the temperature of the surrounding. So given that information, you should be able to solve example 7 on your own. All right, so I want you to go ahead and solve example 7 on your own. It does give you the initial temperature of the soup, and then it gives you a second time of the temperature, so that way you can figure out C and K separately, and then answer that last question. All right, enjoy.